So what makes d metal complexes so interesting? Well, it's the d orbitals, right? There's 5 d orbitals. You all have to know what your d orbitals are, what the functions are, represent them, how to draw them, the axes labeled. Super important as we start diving deeper into this transition metal chemistry, that you know the d orbitals just as well as you do the s and p orbitals. Okay. Um, so here they are. Remember, X, Y, Z, X, Y, X, Z, Y, Z, all are very similar. There's clover-like lobe shapes. They have 2 nodal planes, and they have their lobes in between the axes, right? So coming out in between the axes. X squared minus Y squared is just like the XY. It's in the XY plane, but it's rotated 45 degrees. So the lobe is, all the lobes are on their axes, okay? Z squared is a little funky, but remember Z squared is just an abbreviation for the function 2Z squared minus X squared minus Y squared, which is a linear combination of, of kind of the 2 other orientations of this 2 rotated one. That part's not so important, but you do need to know the shapes of these, be able to draw them, etc. Yeah, here it is. Actually, z squared is shorthand for 2z squared minus x squared minus y squared. And it's a combination of z squared minus x squared plus z squared minus y squared, which would be the other, it would be this orbital rotated 45 degrees, and this orbital rotated 45 degrees and added together. All right, so there's 2 models of transition metal compounds. They are crystal field theory, abbreviated CFT, and molecular orbital theory, we call it MO theory. CFT is less complicated as a result. Not as a result. It's not necessarily true that less complicated things are less accurate, right? I mean, Einstein's theory of relativity, if you really look at it, isn't that complicated, and it's very accurate. But anyway, this is less complicated and is less accurate. MO theory is more rooted in quantum mechanics more deeply, and so it is a little bit more complicated, but it's more accurate. We're going to start with CFT before we dive into molecular orbital theory later in the chapter. So in crystal field theory, this is a model based purely on electrostatics. What's electrostatics? It's point charges. It's the dynamics of point charges, right? So it's all about, Coulomb's law. 2 of the same charges repel each other, and that repulsion goes as the distance squared, right? Our starting point is going to be a molecular metal ion, okay, surrounded by a spherical ligand field. So we're treating this ion as just a positive charge, a point charge. And when I say spherical ligand field, what does that mean? It just means that we're not imposing any geometry other than a sphere onto these ligands right now. And so the ligands are in a spherical environment, just like they are in an atom, okay? And when you have 5 d orbitals in a spherical symmetry, they are all equal in energy, just like in an atom, okay? So that's why I put them all at the same energy here. All 5 of them are all equal in energy. There's the ligand sphere. We're just imagining it as a sphere. Now, ligands never bind perfectly in a sphere or ever in a sphere, but this is just kind of a thought experiment to get us started with crystal field theory, okay? What happens, crystal field theory says, when you have this ligand sphere is that the energy of these 5 d orbitals is going to increase versus the free ion, okay, the ion without the ligands present. Why is that? Crystal field theory is treating everything as point charges. And so it's thinking about electron density on the orbitals of the metal ion. And of course, electrons are negatively charged. And it's also thinking about electron density on the orbitals of the ligands. And so if you bring electron density negatively charged on ligand and electron density negatively charged on metal ion, well, that's electron-electron repulsion. It's unfavorable interaction. It's going to cause there to be an increase in energy. But because it's a spherical symmetry of the ligands, all 5 of these orbitals are still at the same energy. Now you might be thinking this is a little bit of an aside, and we'll get to this point um, more deeply. We'll explore it more deeply later in the chapter. But you might be thinking, well, yeah, electrons and electrons repel each other, but I also know that if I'm talking about 2 sets of valence electrons, I can make covalent bonds, right? Or maybe ionic bonds. And yes, that's true, and that could be a favorable interaction. Crystal field theory doesn't think about bonding in this way. Okay, it's not thinking about making bonds, it's just thinking about electrostatics. So that's the difference. When we get to MO theory, then we'll incorporate that additional point. Okay. Then what you're going to do is once you've thought about, okay, fine, I have this spherical ligand field, what's going to happen when I invoke a certain geometry? The geometry we're going to start with in our discussion of crystal field theory is the octahedral geometry, OH, right? We're assuming right now that all the ligands are the same, so we're OH symmetry. And this is sort of the starting point, okay? So I'm going to stop there and we'll continue in a minute.